Hello, welcome to what I plan to be the last lecture on calibration. So here we're going to deal with basically just a couple of advanced concepts inside of calibration. So we want to talk about the limits of what this method I'm presenting for calibration, like so the limits on what we can do, what we can't do, and I want to talk a little bit about weighting factors, which I've hinted at, but we haven't seen yet. So, all right, why don't we start with weighting factors. So the idea behind a weighting factor is, okay, let's say I have a whole data set. So let's say I take a whole bunch of data to try to calibrate a sensor. And, okay. So I've got a data set. And there's one point here that is suspicious, but I don't know that it's wrong. Maybe the sensor really does do that. Maybe the sensor really does have some higher order polynomial characteristic up at these higher points. Or maybe it's a perfect line and this is just a bad data point and we should throw it out altogether. You can you're not left with only two choices with weighting factors. Basically, I've just presented two extreme alternatives. One where we count it equally with all other data, and we say it's a data point, it has an equal right to be in the data set. And the other one where we say, no, we don't trust it, throw it out. There is an in-between alternative where we say, well, we can't throw it out, but I don't trust it, and I don't want my fit to weight this point as heavily as the others. So if we do that, all we need to do is modify how we calculate error so that not all points are weighted equally. Here's how we do that. So remember what we said was that if I've got some fit, so let's say you've got a series of data points, right? So x and y data points, right? So we have x1, x2, yada yada yada, y1, y2, yada 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 yada. Okay, and we said that we could calculate. I'm going to notate this as so this is my fit function. So this would be y of x1, so y of x2. And I'm going to keep it generalized, right? Because what we're about to do can apply in any case. So remember, we defined error for the kth point, right? 1 to k, all the way out to k. Yada yada yada. We defined error as the difference between the measured value for y and the value I calculate for y with my fit function. All right. Now, we then said we wanted to minimize the expected value of error squared. So before, what we did was we said and we need to minimize this sum by mucking around with the shape of y, by altering the coefficients inside of y until I finally get something that looks good. Okay, so that's what we did before. But now, what if instead we modified this so that here's the place right here where we tally up all the individual squares of errors. But what if we wanted some of the squares to count more or less than others? To do that, we can use a weighting factor. This is not an omega, that's actually a W. w sub k, and then the rest of it is unchanged. So here we'll look at the expected value of the weighting factor of a weighting factor times error squared. So basically we get to individually select. And w, let's keep in mind, w is a coefficient that we made up. The idea is that w can vary from 0 to 1 is the idea. So we can give a relative weight for every individual point. So obviously if the weight were 0, then that error wouldn't contribute at all to the expected value. Whereas if that error, if that weighting factor were 1, then that error would contribute normally, right? And then there's an entire spectrum in between that we can choose from. Okay, and we get to choose that for every individual data point. So that's fine. That doesn't really look that much more complicated when we get over here. So you can see the difference between what we did before and what we're going to do now is just that we get this coefficient that shows up out front. So let's look at an example where we apply that to a linear fit. So let's just reapproach the linear case for the case when we have weighting factors. So the expected value of, oh, whoops, no, silly, I need more coffee. It's a disadvantage of doing this in the morning. You're used to seeing me in the afternoon when I'm properly caffeinated. All right, here we go. So let's just skip to the punchline. There we go. So notice that the only variables that have subscripts, that indicates that these are variables that change with each data point. Notice that m and b do not have subscripts. Notice that n does not have a subscript. Notice that these, because these are coefficients that are global, that's the slope. That's over my entire data set. That's just a number. Whereas these are in lots and lots of individual data points, right? So keep clear in your mind. You want to keep organized in your mind what each of these variables represent. Don't get lost. Don't get lost in just mindlessly applying algebra. You really want to keep in your mind an idea of what everything means and where you're headed, right? That'll keep you from getting these subscripts mixed up. Okay, so the next step, if you'll recall, was we took partial derivatives to construct a system of equations for how to construct a curve fit here. So let's do that. The idea is we want to force this to be true. The partial derivative of my expected error squared will be 0 when I'm optimal, when my choice of m is optimal, and the same will be true when my choice of b is optimal. Well, let's go ahead and evaluate that one. So keep in mind that since this is just a data point, right, it has no partial derivative. When we're taking a partial derivative with respect to m, none of these have a partial derivative except for m. It's the only thing that appears like a variable, so long as we're doing this. That makes this actually pretty easy. So my 2 comes down. I've got to deal with that first. 2 wk. times negative x is the inside derivative. There we go. Not so bad. Actually, it looks just like if you look back at your notes, or you look back at Calibration 1 lectures, you'll see it looks exactly the same as when we took the partial derivative with respect to m, except that there's the w out front. It's really the only difference. So we can manipulate that a little bit. Since we're going to force this to be equal to 0, just like before, we can factor out the 2 and get rid of it. Why can't we factor out the w and get rid of it? Well, because this is a summation across k, and w has a different value for every k. What would you factor out exactly? The number w changes with every value of k. There's nothing in common to factor out. Unless you force them all to be the same, you can't do that. And we're not forcing them to all be the same. So, what we can do, though, is split this up into individual terms. So we can get rid of the 2, and then we can split this into individual terms. Here's what we'll be left with. That's different looking. I'll go ahead and leave my m inside. Weird. Let's get rid of that. All right, we did it. We got our first equation for dealing with a weighting factor. Let's do it again. Let's do it for b. All right, so just like before, when we take the partial derivative of my expected value for error squared, I need to deal with the 2 first. But the only difference is going to be the inside derivative is no longer with respect to m, it's now with respect to b. So this is going to be much simpler. So everything's going to look the same until we get to that inside derivative. Easy. No problem there. Okay. Not a problem. Yeah, so we just distribute our sum. Just like we did before, split it into individual terms. We can get rid of the 2 because of the 0, just like we did before. And the only difference is we're not going to have this x in every single term. So here we go. It's going to look like this. Negative. Oops, forgot my w. Or there we go. We have our system of equations. So the last step to actually solving these is just like it was before. We solve for m, and we're going to get something that looks very much like it did before. So finally, type be paper conscious. I'll use the back of one of these. There we go. Turns out, when you lecture this way, you really go through some paper. All right, so let's find M. It's going to wind up being, after all the algebra, M is going to wind up being this. Yeah. Oops. You know what? You know what? I just goofed. I got ahead of myself. Well, that's what I get for trying to skip steps. I tell you what, why don't we work through it, just to make sure I don't goof. So let's solve for B. Let's actually go through the steps. Let's eliminate B. Let's actually solve for B. Okay, fine. Fine, I won't skip steps. There we go. So we solve for B. B is equal to, we're going to substitute it out. Now that is a little different from last time. In addition to there being w's inside the expected values, that's new, but this w in the denominator is also new. So that wasn't there before. That's going to make this, that's actually, as I started writing, as I started trying to just construct this in my head, I realized I had forgotten this guy, and I had gotten myself into trouble. So I needed to fix that. So that's why we're doing this. Okay, so let's throw it in. I'm just going to start by copying my M equation now. But I'll go ahead and substitute in the B. So here comes the B. And that's all times the expected value of Wx. Alright. Yeah, and so you'll see where I goofed up. I realized I needed an expected value of W here because we're going to multiply everything by this W to get it out of the denominator, just to try to clean it up. And I'm going to distribute some things around. So once we clean this up a little bit, the next step is it should look like this. There we go. And minus M. Cool. And we're very close now. So now I just need to solve. So what I've done is multiplied everything by expected value of W. So you picked up expected value of W here and here, but not in these terms. And then I went ahead and distributed this Wx as well. So that's why you pick it up here, and that's why you pick up a Wx squared here. Okay, so let's solve for M. So we have two sources of M. So 2 doses of M will give us this. Minus this thing here. We need x squared. Beautiful. Now, what's interesting here, and this is actually how I figured out I was making a mistake back up here, is if you look at every term, every term has the appropriate number of x's and w's, right? They're mixed around inside of the expected value operations, but they're all there. Every term has 2 w's. Every term in the numerator has an x and a y. so the units work out. Every term in the denominator has 2 w's and 2 x's. Right? And so the units, even though the values of each term will be wildly different, the units do in fact work out. Isn't that lovely? And then we can, so there we go. That gives you a system that you can solve. And you've got it. And you calculate this the same way you would any other expected value. You just need to tabulate a column for w, x, and y. So if you look at the spreadsheet I've got online, I'm not going to walk you through that because it's a little cumbersome. But if you take a look at the spreadsheet I've got online, that's exactly what I've done. I've given you an example where we actually tabulate columns for w, columns for wxy, wy, wx, and we use that in this formula to calculate a slope, where you can apply a weighting function. Okay, so let's look at a more general form. So the next thing I want to talk about, so the item 2, so more general curve fits. When I've hinted, we've applied this so far to the following cases. We've looked at y of x is equal to mx plus b. Great. We've looked at a cubic. And I've hinted that, well, so this will work for any polynomial, and I have hinted that this will work for a lot of other functions. Well, I guess the question is, what other functions? In reality, in fact, this will work for any linear combination of arbitrary functions. So in other words, this will work for a function that looks like this. And you can have any number of weird, any number of these, any number of weird functions you want. These f's could be anything. We could have, for example, we could have a1 times the natural log of x. We could have a2 times an exponent of x. That's fine. We could have a3 times the sine of 4 pi x. That's fine, no problem. So as long as the things we want to calculate are just coefficients, we're okay. The analysis we've used will work. Where this breaks, so a negative example, oops, there's an exponent. There is a coefficient inside the exponent that breaks this entire thing. You cannot use the analysis we have used to optimize for A2 and hope that it will work. A2 now has a nonlinear impact on the system, and you can't just solve it using matrix math. It's, alas, quite a bit harder. So I can show you a quick example of how that works. So for example, what if let's say we've just got a combination of two arbitrary functions. And keep in mind, whatever you're doing, you can put in whatever you want there, right? So that these can be any functions that you can calculate, you can put them there. All you have to do in order to do this analysis is be able to produce a column of tabulated data for that function. That's easy, right? Even Excel can do that. Even Excel can do that. So, you know, it's even easier if you use like a real language or a grown-up language. Okay, so then the expected value for error squared oops, well, let's write it like this, sorry. I'm using a shorthand that I use for this analysis sometimes that I have not developed, so I should not use it here. There. So there you go. And now we can take the partial derivative to optimize. Oh, whoop, there is no m, sorry. I'll only do it with respect to A1. Doing it with respect to A2, it's the same thing. Shock and amazement. This is going to look really familiar. Now the partial derivative with respect to A1 is just F1, negative. Because when you take a partial derivative with respect to A1, it appears to be the variable and everything else appears constant. So there we go, and that's all divided by n. There it is. And again, because we're going to force that to be equal to 0, we can get rid of the 2, and you end up with this is going to result in the equation inventing coefficients all over the place. Whoops. There we go. So there you go. You've got yourself an equation. And again, so calculating that expected value is easy. You just make a table of f1 of x and square it. And then here you just need, again, this is easy. You just make a table of f1 times f2 and take its average, right? Like that's actually really easy to do. And what appeared to be a really difficult problem, like a really generalist, challenging problem, is not so scary anymore, actually. Okay, and you just have to repeat that again for A2, but I bet you can figure out how that's going to turn out. It's going to look very similar, except the coefficients 1 and 2 will be flipped. And you get a system of equations that's totally solvable. So this is quite general. Now let's see, just for a moment, I don't want to go into, I don't want to go crazy with this idea, but it's worth looking at. Let's look at why it doesn't work. So let's just do well, no, let's do it properly. Let's do that. So let's say you had, for example, your thermocouple lab. What if you wanted to use a regression method like this? What if you wanted to use a curve fitting method like this to try to figure out what the time constant was, the optimal time constant value for your data set from that lab? What if you wanted to try to do that? There's a problem when you use this analysis. So again, my error squared things are looking pretty good when I differentiate with respect to A1. Life turns out actually to be pretty decent when I do that. So here's what you get. Sorry, I forgot my squared. And now I multiply by the inside derivative. Pretty easy, right? Negative. Pretty easy, right? Well, wait for it, and we're going to say that that's equal to 0 because we want to optimize this. All right, so when I try, so things are looking pretty good, right? Until things are looking pretty good until I try to pull out coefficients of expected values in the same way that we have so far. So let's actually write this out and see what goes wrong, because something does. Okay, there's my first term. And then I have, let's see, I'm going to have sum of A1 I'm being a little sloppy there. I could have combined those exponents, but I'm not doing it yet. And that's it. Yeah, sorry. Yeah, this is relatively simple, so that's it. That's all equal to 0. So the problem is A2, I can't get to it. It's trapped inside of this exponent, and I cannot possibly pull it out of the summation. And so we're trapped with this. I can't solve for that A2. It's inside the expected value, and I cannot pull it out. There's no rule of algebra that will allow me to pull that out. I'm stuck. And similarly, I can pull out this A1. That's fantastic. A1. Oh, great. Except I've still got this mess in here. That's awful. Yeah, so this fails. Let me show you a little trick though. So in general, when you've got a coefficient jammed inside of a function like this, you're kind of stuck. You need to use a different method, one we're not going to learn. It's way more complicated, but there are methods to try to optimize those. They're theoretically much more complicated, and computationally, that is, for your computer, they're much more challenging too. They require iteration. So that dives deep into numerical methods. So we're not ready for that. But just know that there are methods out there. You can still do that. For this problem, for just this problem, I'm going to show you a little trick that will actually allow you to get in there. So okay, that doesn't work. But what if I did have the thermocouple and I really did have a set of y values, xk values, dot, 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 yeah. And I really do believe that that's true. Well, fortunately, thanks to the wonderful human beings who taught me high school math, I know that this is true. Isn't that delightful? We've reduced it back to a linear problem. So what if I create a new Now it's a linear problem again. It looks like mx plus b. So what you'd have to do in order to actually use this trick, you would end up with, instead of calculating expected values of y, you'd end up with something that looks like this. A2 would end up being the expected value, that's a nasty expected value sign, expected value of x times the natural log of y minus expected value x, expected value natural log of y, or z, whatever. And we'd end up with the natural log of a1 times, is equal to, rather. Sorry. What did this end up being? Natural log y times a2 minus the expected value of x. Pretty sure that's right. So what I'm doing is just in my head rewriting the result we got from using a linear fit, but I've just switched everywhere I saw. Normally would have written a y, I wrote a natural log of y, and instead of writing b, I wrote natural log of a1, because, well, that's the form this is in. The constant, instead of being b, is the natural log of a1, and the value, instead of being y, is now the natural log of y. And so you could go through that whole process and derive this, or I could just write it. And I've used this before. It works pretty well to get exponential fits. Okay, so I hope this has been good. I'll push out some more examples, and I'll look forward to your questions. Thank you for watching.